So today we're going to be talking about a topic that is mostly an AP topic. So this is going to be a small portion of our material. But it's important because it gives a broad, comprehensive picture of what's going on. Will, if you wouldn't mind closing the door.
I'm here.
And our topic is non-constant acceleration. Now, you may not have thought about it too much, but I've tried to consistently use the words so far. Equations of motion with constant acceleration. And we have 4 of those equations of motion, and you all delivered them on your quizzes. And the first equation is V equals, everybody all together?
V0 plus AT.
That was moderately good. Murmur. Let's have it louder so that you feel confident with it. V is equal to?
V0 plus AT.
There you go. That's right. And then we have 2 different equations that give us displacement, one of them with acceleration, one of them without. The one with acceleration, delta x equals? Nice job, Austin. Delta x is equal to?
V0t plus half AT squared.
There we go. And in case you are tempted to forget your square on this term or the t on this term, keep in mind that the units have to be meters. So we have to multiply meters per second times seconds to get meters. And in this term, we have to multiply meters per second squared times seconds squared to get meters again. So let your units be your guide. And then the one that does not involve acceleration is delta x equals, everybody all together?
V plus V0 2 times t.
Yes, and definitely not minus, as a couple of you had, because what we're doing is we're averaging initial and final velocities to get an average velocity, and then multiplying that times time. And you get meters again. That's right. Good. And the last one, which takes time out of the equation, is v squared is equal to?
V0 squared plus 2a
Plus 2a delta x. That's right. And a couple of you used the form that was in the book, which is perfectly fine, which simply explicitly writes delta x as final minus initial. And I'm okay with that as well. They mean exactly the same thing. Okay? So those are our equations of motion with constant acceleration. But that raises an obvious question. What happens if I do not have constant acceleration? What does that even mean? How do I know if I'm working in a situation that is not a situation of constant acceleration? So let's take a look at some graphs to understand what that might mean. First of all, physically, a constant acceleration is going to be caused by a constant or steady push or pull. So a great example of a constant acceleration would be the acceleration caused by gravity, which is a nice constant, steady pull. As long as you are falling, gravity is going to be pulling on you. Yes, sir?
What's the thing before cause?
Is.
Wasn't sure if it was.
Yeah. No.
I thought it was a B.
Constant AB caused, no. Constant A is caused by a constant push or pull, and gravity is a really good example of that. But another example of that would be a steady push on an object. Perhaps we might have a situation where the car's accelerometer, the gas pedal, is pushed down so that it provides a constant acceleration for the car, at least over a small time period. Mathematically, when we began to analyze data, A constant acceleration always has the same shape of the position and the velocity graphs. And the velocity graph is the easiest one to spot because a situation of constant acceleration will be one in which the graph of the velocity is a straight line, either with a negative slope like I've drawn it here, or with a positive slope. Constant acceleration implies that velocity is linear. No. Now, actually, we already knew that. I don't know if you knew that you knew that, because we know that constant acceleration gives us v equals v0 plus at. And what type of function is that? A linear function. So there you go. And not only that, but also, if I have constant acceleration, then my position, delta x, is equal to v0t plus 1/2 at squared. And if I want to recover the position out of this, then I can write that as x minus x0, so that the position is going to be x0 plus v0t plus 1/2 at squared. Now don't worry about the parameters xo and vo and 1/2 a. Look at the variable t. What type of formula, what type of equation do we have? It's quadratic, that's right. And therefore, my shape for x versus t is always going to be a parabolic shape. Mathematically, constant acceleration looks like this every time. Now, if I have a positive acceleration, then my velocity will be linear with a positive slope, and my position will be quadratic or parabolic with an upwards concavity, we call it, curving upwards. But the shape of it is the same every time with constant acceleration. Does that make sense to everybody? This is the situation that happens for us approximately 85% of the time in physics at the level that we're working at. When you step out into the wider world of physics, this situation happens about 10 to 15% of the time. Most of the time, that's only because we're approximating. So the question is, how do you handle that larger world? And I'm going to give you just a small taste of that today. If you want the full treatment, come to AP Physics next year. Have a plan. Okay? So what does non-constant A look like? Non-constant acceleration can take a wide variety of forms. We might have a velocity graph that represents the velocity of an object on a spring that has been pulled, and now the object is going yoing, 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 like that. And so the velocity is going to go up, and it's going to go down, and it's going to go up, and then it's going to go down, blah, blah, blah. This is definitely not a linear function. Actually, my velocity would have to go negative sometimes, wouldn't it, if the object is going to go back and forth? Or maybe we're looking at the acceleration, the acceleration of, or the velocity of a football player who has just been hit by a linebacker. And so the velocity versus time might look something like this, where the football player is going, 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 and all of a sudden he's hit, and boom, he's now down. He goes backwards a little bit, and then he stops. So that's definitely not a straight line. That's definitely non-constant acceleration. Okay? So now the question is, how are we going to analyze that kind of situation? And for our purposes, we are going to appeal to graphical analysis. Now, did you guys all get a chance to watch the video last night? And you learned a little bit about that. I'm going to rehearse that. But if you didn't get a chance to watch it, you're going to want to go back. There's 28 minutes of good stuff on how to read graphs. Okay? So our basic analysis methods are going to be we're going to look up values on the graph. We're going to calculate slopes, and we're going to calculate areas. And if you actually can do these three things pretty well, then you're going to be really well positioned to do calculus as well, because what we're really doing is sort of baby calculus. You're not babies, but it's like the first steps of calculus. Okay. All right. So how does this looking up of values work? Let's actually get a graph on the table here. And let's consider a situation where we have non-constant velocity. Let me do it something like this. There we go. All right, so we have a non-constant velocity that looks like this. And so now we want to ask some different questions. We might ask the question, what is the velocity at time 4? This is a lookup question. How do I know that it's a lookup question? Because the axis that is given to me here, the vertical axis, is velocity. And the question is asking me about velocity, the same thing that's on the axis. So the velocity at time 4 is simply a matter of looking up at time 4, what is the velocity? And if this is 2, then the answer is 2. Now we need units. Meters per second and seconds are going to be the usual units of choice. Okay, so analyzing from the graph, we're going to have 2.0 meters per second. Why 0.0? Because it looks like my dot is right on the line right there. If my dot had been, say, up here, right there, then I would call it 2.2, 2.4, whatever. Rule of thumb is that you get 2 significant figures out of a graph. If your graph is really big, then you can get 3. How are we doing so far? Okay. Now, related to this lookup question is the idea of analyzing signs of velocity. I want you to observe that all of the values of velocity here are positive, from 0 all the way out to about 5.8. So we can mark those as positive values of velocity. Question. No. Good? Okay. She had the look of concentrating intently, and I wasn't sure if that meant that there was a problem. But she's good. Likewise, all of the values of velocity from 5.8 and beyond are negative. They're below the axis. And then right here at 5.8, we have we'll call it a critical point. The velocity at 5.8 is 0. So I can mark the velocity as positive from 0 to 5.8. I'm using the mathematical notation. The closed bracket means we include 0. The open parenthesis means we do not include 5.8. And then my velocity is negative from 5.8 to 10, including 10, but not 5.8. Now, how does that help us? Because now it gives us a sense of the motion of the particle. The particle is moving. I can interpret positive velocity is as the particle is moving forward, or t's between 0 and 5.8. If you prefer to use inequalities to express that fact, you could express it like that. People, there's just 2 different styles, they mean the same thing. For t's between 0 and 5.8. And the particle moves backwards for t's between 5.8 and 10, or again, I can express it like this. Notice that I am including 10, but I am not including 5.8. So in terms of analysis of the motion of the particle, this is a pretty complete analysis right here. And it really happens in two steps. First, I determine signs of velocity, and then I interpret those signs of velocity in terms of forwards or backwards motion. If I know that my particle is moving in a vertical direction, then I would interpret positive velocity as moving in the positive direction, which is often up, and I would interpret negative velocity as moving in the negative direction, which is often down. Okay. It's all about your reference frame. Whichever way is positive, that's what velocity means. Positive velocity. Sometimes students will want to short circuit this process. They will say, I'm not going to bother with this plus and minus thing. I'm just going to look at the graph and guess. When they do that, they screw up every time. Because if you look at this velocity graph and just try to read it, you might think that the particle is not doing anything, and then all of a sudden it goes backwards and then it's not doing anything. And that's the wrong interpretation of the graph. That's confusing velocity with position. This is not a position graph showing where the particle is. The particle doesn't stay at 3 and then go backwards and stay at -1. The particle is moving according to this velocity. So the velocity graph is a little bit more abstract than the position graph.
What do you think the acceleration stay the same for each point? The first.
That's a great question. We haven't talked at all about acceleration yet when we're about it. We're talking about just velocity because this is a graph of velocity.
I thought we were talking about that acceleration.
Yeah, no, haven't got there yet.
So it would be constant, then decreasing, and then it would be 0, and then we'd go
Negative.
negative.
That's right. That's right. So this is a constant velocity of 3 meters per second. And then we come to a, how do I interpret the 0 velocity right here at 5.8? What does that mean? It's stopped. That's exactly right. So if I were to act out this velocity graph, it would be like this. I would first move forward with a constant 3 meters per second, then I would slow down to a stop at 5.8 seconds, and then I would move backwards and going a little bit faster until I get to -1 meter per second, like that, and then whatever happens after 10, we don't know. Please notice that at the end of the graph and at the beginning of the graph, the particle is not necessarily stopped.
Usually that's when we just started tracking it.
Bingo, that's right. This is only when the camera starts, and this is only when the camera stops taking samples. It has nothing to do, what happens at the end here and here has nothing to do with the actual motion of the particle. It just means that we lost track of the particle. Okay? So please don't tell me that the particle starts moving at t equals 0. We don't know that. Okay? Good. Cool. All right. Now let's talk about acceleration, because it turns out that we can read acceleration off of this graph also. And that's the idea of slope. We'll do this in a slightly different color. Slope. The meaning of slope can be found, first of all, by looking at the axes once again. When I look at the axes, the slope of any line, let's say I have 2 points on this line from 1 to, let's call it 6, something like that. Hello. Boston. Here, just pass it. Take one and pass it down. Okay. So the slope can be figured out from the axes. If I take these 2 points and connect with that line right there, then the slope of that line is the rise over the run, which is the change in the vertical over the change in the horizontal. And we get that expression straight from reading the axes. There's no guesswork about it. We just look, boom, boom, delta V over delta T. Now that we have written that expression, we interpret it according to physics. What is our physics term for delta V over delta T? Acceleration. And in particular, it is an average acceleration, because it's between or over a time interval, in this case from 1 to 6. And now I can just compute that the same way that we would any other slope. I go to point 1, which is point 1 comma 3, and I go to the point 6, which is 6 comma like negative 0.2, something like that. And I do final minus initial. Please notice that the final one is always the one furthest to the right because it is later in time. And that gives me negative 3.2 divided by 5. And the units come straight off the axes. There's also no guesswork with the units. It's just a matter of reading it directly from the axes. And negative 3.2 over 5 is going to be something like negative 0.64. I cheated. I multiplied by 10, or multiplied by 2 and divided by 10. And that gives me an average acceleration of negative 0.64 meters per second squared. If I need an instantaneous acceleration at some time, I will do the same thing, but I will let delta t go to 0. In other words, I'll find the slope at a single point. So I come back here. Let's say that I want the acceleration at t equals 4. Then I would go and I would put a line that goes in the same direction as the curve at t equals 4. If your curve already happens to be a straight line at that point, then your curve is that line. And so at t equals 4, my tangent line is the curve. And so I can read the slope here. In fact, I often just do it directly on the graph. I would say the slope here has a run of about 3 and a rise of about negative 3, maybe a little bit more than that. And so I would say that the acceleration at 4 is simply negative 3 meters per second over 3 seconds, which is negative 1.0 meter per second squared. So we have slope as acceleration on our velocity graph. And that can either be average if it's over a time interval, or it can be instantaneous if it's at a point.
So the instantaneous would be the non-constant acceleration.
What non-constant acceleration means is that the instantaneous acceleration will be different values at different times. That's right. So if I were to compute the acceleration at this point, at t equals 1, the slope of the curve at that point is 0. And since 0 is different from negative 1, that means my acceleration changed from 1 to 4.
But if you average that whole thing into one acceleration, is that just constant?
That's a great question. If I average the whole thing, then what I'm getting is a value that is the average over the entire thing. And that average would tell me over the entire time interval what my change in velocity is over the entire time interval. So computing an average implicitly says, let me treat it as if it were a constant, even though it isn't really. Yeah. Go ahead.
If the acceleration is then like a straight line, we just have to estimate it.
Yes, that's right. You just are going to estimate. And that's why graphs really only give you 2 significant figures. Because you're always estimating off of graphs. You actually do that with the points too, right? You're estimating about where the number is. Question? Okay. How are you doing? Are you comfortable with the slope idea? Okay. Good. Good. Okay. Well, so that's slope. Let's come back, and I want to take this same motion graph, if I can. I'll try. That was -1.7 and 3.3. Okay, so here is my velocity graph reproduced And of course, we have positive here, and we have negative here. So the velocity graph can also give us displacement through computation of area. If I take a look at the area under the curve from here to here, all of this area right here, then I can think mathematically of this area as being computed by a bunch of little tiny rectangles that cover the entire area right here. So picture a bunch of rectangles, and now the rectangles start shrinking and height. Okay? And each rectangle is going to have an area that I can consider to be delta t, a little chunk of time along the time axis, multiplied by the velocity at that time delta t.
So you could make the two rectangles have whatever size you wanted to get
The area as precise as you want. That's exactly right. And so I can say that mathematically, the area is going to be equal to velocity times delta t for each time interval, and then we add them up. And the capital Greek sigma, which is not an E, represents the sum of all the velocities times times. Now, that's mathematical. Physically, here's what this does for us. This is v0 times t, except that my v at each point is different for each different velocity. Yes?
Sorry, do you know how to
About 40, 43. Yeah, big question. Okay? So if I compute this area, then what I'm doing is adding up rate times time, and you already know that rate times time is simply displacement. So the area of one little rectangle would tell me the displacement during that time interval. Let's actually put numbers to it. This rectangle looks like it is about a quarter of a second. Let's call it 0.2 seconds. And the velocity here looks like it is about 2 meters per second. Now it looks like it's about 3 actually. Okay? So if I were to take the 3 meters per second, and during that time interval, 0.2 seconds, and multiply those, then that would give me a displacement of about 3 times 0.2, or about 0.6 meters. And what that's saying is, during that small time interval, we went 0.6 meters. During a different time interval, let's say 0.2 seconds like here, my velocity was faster, it was 4 meters per second. So 4 times 0.2 is 0.8 meters of displacement during that time interval. If I now take all of those time intervals that I compute for all of those different seconds between 0 and 6-ish or whatever, then that gives me the total displacement for the entire thing.
On the test report, are you going to give us an exact first time?
Yes. So the question would be phrased something like, find the displacement, find delta x on the time interval 0 to 5. And so then you would take your curve, your velocity curve here, and you would go from 0 to 1, 2, 3, 4, 5, like so. You would say that your area of this shape right here is equal to that displacement. Now, I might give you the exact heights or something like that. But if you have a graph, you don't even have to work that hard because you can count squares. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, not that one, 15, 16, 17, and 8.
Well, some graphs tend to be like that big.
With this graph, you just take the first 30 and do that as a block, and then do the...
Yes, absolutely. That's right. If you can find simple shapes such as rectangles or triangles, go for it. Yep.
So for the little rectangle we put there, the displacement for that is the displacement for the entire 5 seconds.
Yes, that's exactly it. What you've done is I picture it like this. You're starting here and you're adding up displacements as you go.
And for like linear and quadratic functions, are going to give us the equations since that's fine.
Yeah. See, Jesse knows some calculus shortcuts. And if you happen to know calculate shortcuts, I have no objection to using those.
Do you get the equations?
Rarely. Because if I were, then all that would do is confuse matters for people that don't know the calculate shortcuts. So if you want to model it as a quadratic and it looks really pretty parabolic, then I'm okay with that. But that's really kind of up to you to do. You can take the data and turn it into a reasonable model. Okay, so what happens if I ask a slightly different question? If I want delta x on the interval 5 to 8, something like that. Well, if I look at 5 to 8, now here's my velocity curve, and so I start at 1, 2, 3, 4, 5, and I go to 6, 7, 8 right here. Ooh, thank you. And what I notice is that we have now gotten ourselves into a situation where we have some of my area above the axis and some of my area that's below the axis representing negative velocities. So we're going to interpret those negative velocities as giving us backwards displacement. If I'm moving to the left, yes, then I would get negative meters of displacement out of it. So I'm going to actually break this up into two pieces. This piece right here is a triangle, and so I'm going to say that its area, I'm going to write, first of all, the notation that I'm going to write is delta x equals the sum of v delta t. That's how you write what you're doing. Now we're going to come back and compute it as the area of the little triangle, which is 1 meter base times height. It looks like it has a base of about 1 second and a height of about 1.5 meters per second. And then I'm going to add to that the area here of this guy, which looks like it is about 1.5 total area, 1 square plus a half square, and I'm going to count that as a negative. And so that gives us a half of 1.5, or plus 0.75, minus 1.5 is negative 0.75 meters. And the way that we interpret this is like this. We made some forward progress of 0.75 meters, but then we wiped it out with negative displacement of 1.5 meters, so that the net total displacement was negative 0.75.
When the velocity is negative, where does the time go?
When the velocity is negative, the time is still marching on in the positive direction. So positive times negative gives us negative. Yeah, good question. Can we do the same stuff on a position graph? We can do 2 out of 3. On a position graph, I can look up positions. I can also compute slopes. What is the slope on a position graph tell me? Velocity. And you can tell that from the axes, delta x over delta t. But if I try to compute area on a position graph, I get something that doesn't really make any sense. What does it mean to have units of meters seconds? No idea. So we could mathematically compute that area, but we don't really know what to do with it. It doesn't make any sense. Okay? This was a much more abstract kind of a lesson than we've done for other things. So I encourage you to go back and either listen to this again or to go back and watch the first video where I talk more specifically about some of those details. But I think you've got enough to go with for your homework and so on and so forth. And then keep thinking about this, because we're going to use areas and slopes again in the future as we consider other types of physical quantities. Yes, sir.